Welcome to section 2.1, which is triangle trigonometry. So triangle trigonometry. So let's recall from the previous sections. So recall. So in a 45, 45, 90 right triangle, so in a 45, 45, 90 right triangle, the ratios of side to hypotenuse, of side to side to hypotenuse, are given by remember it's 1 to 1 to root 2, so 1 to 1 to root 2. So what does that mean on an actual picture of a triangle? So let's draw a 45, 45, 90 right triangle. Let's see. So here's my 45, 45, 90 right triangle. So let me zoom in. So this angle up here is 45 degrees, as is this angle down here, 45 degrees. Okay. So what that means is if my sides have length 1, then the hypotenuse has length square root of 2. Okay, and next we had in a 30, 60, 90 right triangle. So in a 30, 60, 90 right triangle, 30, 60, 90 right triangle, So the sides, the ratios, let me put it that way, the ratios of small side to long side or large side to hypotenuse are given by that was 1 to the square root of 3 to 2. Remember, square root of 3 is less than 2 because 2 is the square root of 4. Okay, so what does that mean? We've got a triangle that looks something like so. Not drawn to scale, but approximate. Okay, so the smaller angle measures 30 degrees. The larger angle measures 60 degrees. Okay, so if the small side has length 1, the larger side will have length root 3, and the hypotenuse will have length 2. And then we did derive in an example the ratios. So in a 15, 75, 90 right triangle, I'm just going to bring this up because it will come back somewhat later on. Right triangle, the ratios of small side to large side, and by side I mean leg, large side or leg, to hypotenuse, hypotenuse is given by now this is a larger ratio. So the two smaller ratios had root 6 and root 2. So the small side had root 6 minus root 2. all over 2. The long side had root 6 plus root 2 all over 2. And the hypotenuse was simply 2. Now, of course, let me be quiet. I'll get to that later. Okay, so let's draw a triangle. A 15, 75, 90 right triangle. So here's our right angle. The small angle here will be 15 degrees. The larger angle up here will be 75. Okay, so what this means is that the small side is going to have a measure of root 6 minus root 2 all over 2. Then the long side will have a measure of root 6 plus root 2 all over 2, because it's larger, so it's plus, not minus. And the hypotenuse is simply 2. Okay, so let's consider the following. So consider a random right triangle. So right triangle. Well, why can I not write? Triangle. Let's call it triangle ABC. Okay, so I'm just going to draw a random right triangle. Okay, so I'm going to have A here, B here, and C here. So let's have theta be here. Now notice theta is cutting through the hypotenuse and side AC. So I'm going to call AC. So theta touches AC, right? So theta is adjacent to side AC. But now let's look at BC. Notice that theta doesn't cross that side at all. So it's not touching BC at all. So in that case, we say that theta is opposite to side BC. Okay, when theta doesn't cut through the side, now the hypotenuse is its own object. So hypotenuse AB. So how shall I say this? We know that AB, this line segment here, is the hypotenuse. So we only talk about theta with respect to the adjacent or opposite side. We don't really focus on the hypotenuse. Okay, so that's just some terminology there. Okay, so definition. So an angle theta in a right triangle. So an angle theta in a right triangle is, number 1, adjacent. That's our first definition, adjacent to the leg it touches, to the leg it touches. And the other definition was opposite to the leg it doesn't, right? Opposite to the leg it doesn't touch. It doesn't touch. So when you're opposed to something, you don't want to touch it. Okay, so it's opposite. Now, another definition will be triangle trig. So how do we do our 6 trigonometric functions with respect to a triangle? So let's let theta be strictly less than 90 degrees in right triangle ABC. Just like we have right here. Okay? And let's make sure we have that the measure of angle C is our 90-degree angle. Not that it matters for this definition. Okay, so number 1. Sine of angle theta, which we used to have as y over r, is now going to be, it's going to be the opposite side, opposite, over hypotenuse. Hypotenuse. So without thinking, we already know what cosecant of theta is. So cosecant of theta just flips this upside down. So we know that this will be hypotenuse over opposite. Hypotenuse over opposite. So at least I don't have to think to create those. So the next definition would be sine of theta. Sorry, cosine of theta. I already did sine. Cosine of theta. Well, cosine is going to be adjacent. So adjacent side over hypotenuse. So we can easily evaluate secant of theta by just flipping cosine upside down, namely hypotenuse over adjacent. Hypotenuse over adjacent. And last but not least, tangent. Well, tangent of theta is the quotient of the two above. Notice the word hypotenuse reduces, and we are left with opposite in the numerator, opposite over adjacent in the denominator. Hence, cotangent, the reciprocal, just flips this upside down. So cotangent of theta flips that ratio upside down. So we will now have adjacent in the numerator and opposite in the denominator. Okay, so for example, so let's let triangle ABC be given. So let triangle ABC be given, which I will give you in a moment. So evaluate the 6 trigonometric functions of theta. Evaluate the 6 trigonometric functions, which I'm just going to call trig functions, of theta. Functions of theta. So let's draw our right triangle. Like so. Let's say I have 3, 4, and 5. And let's put theta down here. Okay, so sine of theta is going to be opposite to theta. So opposite to theta is 3 divided by hypotenuse. So the hypotenuse is 5. In fact, I'd like to change, well, hopefully you can see this. I think I'm going to change to orange just to make it a bit darker. So for us, let's use hypotenuse orange. Okay, so now without further ado, I can find cosecant fairly easily by just taking the reciprocal. So this will be 5 over 3. Similarly, we can evaluate cosine of theta by taking the quotient of adjacent to theta, meaning the side touching theta, which in this case is 4, over hypotenuse, which is 5. Therefore, the reciprocal secant is namely 5 over 4. We just flip it upside down. So we get 5 for the length of the hypotenuse and 4 for the length of the adjacent side. So last but not least, tangent of theta is the quotient of the two guys above. Notice the 5's reduce, and I'm left with 3 over 4. Taking the reciprocal for cotangent of theta, I get 4 over 3. That is blue over purple. Okay, so hopefully this is making sense. So now let's consider. Once again, I'm going to draw some random right triangle. So let's consider right triangle ABC with opposite sides, little a, little b, and little c respectively. Okay, so what does that mean? That means we have a triangle that looks something like so. Any right triangle. So we have A with opposite side little a, B with opposite side little b, and C at the right angle with opposite side hypotenuse little c. Okay, what I'm going to do is I'm going to call the angle here, down here, alpha. And I'm going to call the angle up here beta. I know that alpha plus beta plus c is 180 degrees. So alpha plus beta plus the measure of angle c is 180 degrees. Okay. Well, alpha plus beta plus 90, because that's the value of the right angle, 90 degrees, is 180. So let's subtract 90 degrees from 180, so let's think about it. 18 minus 9 is 9. So alpha plus beta is 90. So we have alpha plus beta is 90 degrees. So are these complementary or supplementary, given that C comes before S and 90 is smaller than 180? So that means that these are complementary angles, right? Complementary angles, right? Alpha and beta, because they sum to 90. Okay. So let's note color should I use? If I have sine of alpha, that's going to be the opposite to alpha, which is little a, over hypotenuse c. Okay, in fact, alpha was darker blue. Let me make sure I get the right color blue for alpha. What about cosine of alpha? So cosine is adjacent to the angle over the hypotenuse. So the side that's touching alpha is b over c. So tangent of alpha tangent is just a quotient of the two guys above. The c's reduce and I get a over b. Now what I'd like to do is take the reciprocal functions beneath these. The reciprocal to sine is cosecant. So cosecant of alpha is going to be flip sine upside down. So hypotenuse c over opposite side a. The reciprocal to cosine is secant. So secant of alpha is going to be hypotenuse over adjacent side b. And last but not least, cotangent of alpha is going to be the reciprocal of tangent, namely b over a. But now let's do the same analysis for beta. So sine of beta sine of beta is opposite to beta, which is little b. That's the side beta is not touching over hypotenuse c. Cosine of beta is going to be adjacent to beta, which is side a, over hypotenuse c. Tangent of beta is just the quotient of the two above. So hypotenuse c reduces, and I get b over a. The reciprocal functions, cosecant of beta, I'm going to flip sine upside down. So when I do that, I get hypotenuse c over a opposite to beta b. And now secant of beta, I'm going to flip cosine upside down. So what that's going to give me is hypotenuse c over adjacent a. And last but not least, we have cotangent beta. We'll just be flipping tangent upside down. So that's going to be a over b. So why did I do all of this? Well, let's notice something. That sine of beta is the same as cosine of alpha. So that's interesting. I can say, okay, well, this is equal to cosine of alpha. Copy, paste. Okay, thank you, Apple. Okay, well, let's look at cosine of beta. Cosine of beta is the same as sine of alpha, right? So I can say, okay, well, this guy must be equal to the same thing as sine of alpha. Copy, paste. That's interesting. So it's like cosine and sine swapped places. Okay, let's go down to cosecant for a bit. I'm going to skip tangent for a second. Let's look at cosecant of beta. Well, that's the same as secant of alpha. Okay, so I can say cosecant of beta is the same as secant of alpha. Oops, I guess I didn't copy anything. Copy, paste. Oh my goodness, what happened? What is going on here? Oh. Okay, so there we are. Now let's look at secant of beta. That looks like it's the same as cosecant of alpha. So I can say, okay, well, secant of beta is the same as cosecant of alpha. So it looks like secant and cosecant have swapped places when it comes to swapping alpha and beta. But now let's look at tangent. Because tangent of beta, b over a, is the same as cotangent of alpha. So I can say, okay, this is the same as cotangent of alpha. And, of course, you know what's coming next. Cotangent of beta must be the same as tangent of alpha. So I can say, okay, this is equal to tangent of alpha. So what is this all about? What am I going on about? Well, definition. Do I have enough room? Yeah, okay, so definition. So these sets of trigonometric cofunctions, cofunctions, that's what we're defining, cofunctions, differ solely by the prefix co. They are number one, sine and cosine. Number two, that's a terrible dot. Number two, tangent and cotangent. And number three, secant and cosecant. Okay, so these cofunctions, notice sine and cosine, tangent and cotangent, secant and cosecant. So these are the three groups of cofunctions. But what's interesting, look, sine and cosine cofunctions were grouped here. Tangent and cotangent cofunctions were grouped there. Secant and cosecant cofunctions were grouped there. So that leads us to a theorem. We saw that cofunctions of complementary angles, are equal. So did we have that alpha and beta were complementary angles? Sine and cosine are cofunctions. So cofunctions of complementary angles are equal. That is, so what we have is, we could say sine of 90 degrees minus theta is the same as cosine of theta, and vice versa. Or we could say that tangent of 90 degrees minus theta is the same as cotangent of theta. Or we could say that secant of 90 degrees minus theta, make that 90 a bit better, is going to be the same as cosecant of theta, because cofunctions of complementary angles are equal. Okay, and where did I get that 90 minus theta? Well, do you agree that if alpha plus beta is 90, then alpha is 90 minus beta? Same thing. Okay, so for example, let's actually show this. So example, so consider a 30, 60, 90 right triangle. So consider a 30, 60, 90 right triangle. So let's show that. Sine of 90 degrees minus theta is cosine of theta. Tangent of 90 degrees minus theta is cotangent of theta. And last but not least, secant of 90 degrees minus theta is cosecant of theta. For theta equals to, let's just do 30 degrees, shall we? Maybe, and theta equals to 60 degrees. Let's kick it up a notch, shall we? Okay, well, this is a 30, 60, 90 right triangle. So let's draw a 30, 60, 90 right triangle. What do I know about the ratios of the sides in a 30, 60, 90 right triangle? So the small angle is 30. The large angle is 60. Okay, so we know that the ratios are 1 to the square root of 3 to 2. Okay, so let's look at this. So if I were to evaluate sine of 30 degrees, 90, actually let me be more thorough. So theta equals to 30 degrees. Let's evaluate this one first. So in that case, sine of 90 degrees minus theta that's going to be sine, what's 90 degrees minus 30? That's 60 degrees. So that'll be a ratio. So actually, I should be more thorough. Let's be obnoxiously thorough, shall we? 90 degrees minus 30 is sine of 60. I guess I didn't need to be that thorough, but what the heck. Okay. 30. So what is sine of 60 degrees? Well, here's 60. So sine is opposite side. So the opposite side to 60 is root 3. And the hypotenuse is 2. So that's sine of 60. What about cosine of theta? Well, that's going to be cosine of 30 degrees, right? So cosine of 30 degrees is going to be a ratio. It's going to be adjacent to 30, which is root 3. Oh, I guess I should have given myself more room here. Move this down a bit. So do we agree the side adjacent to 30 is root 3? And the hypotenuse is 2, so check mark. So they are equal. Now let's do tangent. So let me make this better color. So tangent of 90 degrees minus theta will be tangent of 90 degrees minus 30 degrees in this which is tangent of 60 degrees, which will be a ratio. Okay, so let's look at that. So tangent of 60, here's 60, is opposite side over adjacent side. So that's going to be the square root of 3 over 1, or just the square root of 3. Cotangent of theta is going to be cotangent of 30 degrees. Okay, well, cotangent is adjacent side over opposite. So 30 degrees. The adjacent side, the one it's touching, is root 3. And the opposite side is 1. So check mark. They're both the same. Okay, so last but not least, let's evaluate secant. Where am I? Where should I put this? So secant of 90 degrees minus theta is going to be secant of 90 degrees minus 30 degrees, which is secant of 60 degrees. Okay, so theta 30. Okay, so secant of 60 degrees is going to be hypotenuse over adjacent. So that's 2 over 1, or just 2. Now let's evaluate cosecant of theta, which will be cosecant of 30 degrees. Okay, so cosecant, that's a reciprocal to sine. So that's going to be hypotenuse over opposite, which is 2 over 1. Check mark. It does work. So all of these do work. But now let's see it for theta equal to, let's have theta being equal to 60 now. Let's do the same analysis. So let's evaluate sine of 90 degrees minus theta, which is going to be sine of 90 degrees minus 60 degrees, which is sine of 30 degrees. Okay, so we have that theta is 60 degrees. Okay, so let's look at sine of 30 degrees. Here's 30 degrees. The opposite to that is 1. Hypotenuse is 2, so this is 1 over 2. Well, now let's consider cosecant of theta, which is cosecant of 60. Okay, so cosecant of 60 degrees. Here's 60 degrees. It's going to be hypotenuse over opposite. So that's 2 divided by the square root of 3. Did I do something wrong? Sine of 30 is cosecant of 60. Oh, cosecant of 60. I'm using the wrong side. Here's 60. Wait. What did I do? Sine of 30 is 1. Oh, because no wonder I'm using cosecant. I'm not using cosine. Sorry, I wasn't using the co-function. I was using the reciprocal. No wonder that wasn't working out. Okay, cosine of theta will be cosine of 60. Okay, hopefully that'll work out better once I write this correctly. Okay, so 60 degrees. Now cosine of 60 should be right, because here's 60. So cosine is adjacent over hypotenuse, which is indeed 1/2. Okay, thank goodness. There we go. Moving on, so tangent of 90 degrees minus theta is going to be tangent of 90 degrees minus 60 degrees, which is tangent of 30 degrees. Theta 60. Okay, so let's look. Tangent of 30 degrees. Tangent is opposite over adjacent. So that's going to be 1 over root 3. So we have 1 over the square root of 3. So now let's evaluate cotangent, the co-function. See if I can get it right this time. Cotangent. Okay, cotangent of theta is cotangent of 60 degrees. So cotangent of 60 degrees is adjacent over opposite, which is 1 over root 3. So check mark, that is indeed what we were looking for. So last but not least, let's evaluate secant of 90 degrees minus theta, which is secant of 90 degrees minus minus 60 degrees, which is secant of 30 degrees. Okay, so let's look at this triangle. Secant of 30 degrees is hypotenuse over adjacent. So that's 2 over root 3. So 2 over the square root of 3. And now the, not the reciprocal function, but the cofunction. So cosecant of theta will be cosecant of 60. Theta, 60. Okay, so what do we get for cosecant? Cosecant of 60 is going to be hypotenuse over opposite. So that's going to be 2 over root 3. Guess what? That's exactly what we're looking for, thank goodness. Check mark. Okay, it does work. So cofunctions of complementary angles are equal. Let's see how much space I have. Okay, so let's do a quick example. So let's evaluate the 6 trigonometric functions. Evaluate the 6 trigonometric functions, or the 6 trig functions. Trig functions of theta equal to 45 degrees. Okay, so 45, 45, 90 right triangle. It's going to look something like so. Oops. So I'm going to have a 45 degree angle down here and a 45 degree angle up here. And in a 45, 45, 90 right triangle, the sides are in a ratio of 1 to 1 to square root of 2. Okay, so let's go ahead and just use the 45 degrees on the bottom. So what is sine of 45 degrees? Well, if I'm looking down here, that's going to be opposite over hypotenuse. But let's go ahead and rationalize this. So let's multiply top and bottom by the square root of 2. So I get the square root of 2 in the numerator, and then square root of 2 times the square root of 2 gets rid of the radical. So it's the square root of 2 over 2. So cosecant of 45 degrees. I'm going to go ahead and flip 1 over root 2 upside down. So cosecant is simply root 2. Cosine of 45 degrees. Well, if I use this same angle, not that it matters, it's going to be adjacent 1 over hypotenuse root 2. So once again, I can rationalize this. Square root of 2 divided by the square root of 2. So what I get then is the square root of 2 divided by 2. If I flip this upside down to find secant of 45 degrees, once again, what I'm going to do is I'm going to use this expression for cosine, flip that upside down, and just get root 2 over 1, or root 2. So last but not least, tangent of 45 degrees. Tangent to 45 degrees is really nice. It's just the quotient of the two guys above him. Anything divided by himself is 1. And what's more, the reciprocal to 1 is simply 1. So cotangent to 45 is also 1. Okay, so with that said, let's look at the standard trigonometric values. So these standard trigonometric values. Standard trigonometric as a table, metric values. Okay, so let's see. Let's have theta. Then 1, 2, 3. Nope, I don't have enough room, but maybe I can figure this out. Let's see. Maybe I'll make enough room. Okay, so first I want to evaluate sine of theta. Then I want to evaluate cosine of theta. Then I want to evaluate tangent of theta. Then I want to evaluate the reciprocal functions, cosecant of theta, secant of theta, and finally, let's see, cotangent of theta. Okay, so let's have theta being equal to, let's see, 2, 3, 4. No, I don't have enough room. So I'm going to do 1.5 blocks. I think that'll work. 2, 3, 4, and 5. Yes, this will work. Okay, good. Because this is an important table. So notice I'm taking my time with it. Okay, what am I doing? Trying to get it right. Okay, so let's have the first angle, theta, be 0 degrees. So sine of 0 degrees, remember that was a quadrantal. The y-coordinate there was 0, so 0 divided by radius is 0. Cosine of 0 degrees was radius divided by radius, or 1. Tangent, which is the quotient of the two that preceded it, namely sine over cosine, is 0 over 1, which is 0. So now let's take the reciprocals. Cosecant is 1 over sine, but thou shalt not divide by 0, so cosecant of 0 does not exist. Secant is 1 over cosine, 1 over 1 is just 1. Cotangent is 1 over tangent, 1 over 0 does not exist. Okay, so now let's move on to 30 degrees. Sine of 30 degrees. Okay, sine of 30 degrees. Where is sine of 30 degrees? Oh, there it is. Sine of 30 degrees is 1/2. We just found this. Cosine of 30 degrees, well, that's also up here. Cosine of 30 degrees is root 3 over 2. Root 3 over 2. So tangent will be the quotient of those two, namely 1 over root 3, because the 2's reduce, and I don't need to rationalize this one. Now let's do the reciprocals. Cosecant is a reciprocal to 1/2, or 2. Secant will be 2 over root 3, the reciprocal to cosine, and tangent will be root 3. Sorry, cotangent will be the reciprocal to tangent, which is root 3. Okay, let's do 45 degrees now. So sine of 45 is, let's use this one, root 2 over 2. Square root of 2 over 2. Cosine of 45, where is it? Is also the square root of 2 over 2. So square root of 2 over 2. Tangent is the quotient. Anything divided by himself is just 1. The reciprocal functions of the unrationalized forms were just root 2. So both cosecant and secant are root 2. And cotangent is 1. So now let's look at 60 degrees. Sine of 60 degrees. Sine of 60 degrees is root 3 over 2. Okay, root 3 over 2. Cosine of 60 degrees, well, that's right here. That's 1/2. Okay, so 1/2. Tangent is just their quotient, so the 2's reduce. And I'm left with root 3. So now the reciprocal functions, flip sign upside down for cosecant. We get 2 over the square root of 3. Let's flip cosine upside down for secant, so we get 2 over 1, or 2. And for cotangent, we get 1 divided by the square root of 3. Okay. 90 degrees, we're almost there. So sine of 90 degrees was radius over radius, or 1. Cosine of 90 was 0 over radius, or 0. Tangent is going to be 1 divided by 0. That's illegal, so it does not exist. Thou shalt not divide by 0. Cosecant is 1 over 1, which is 1. Secant is 1 over 0, so that does not exist, because thou shalt not divide by 0. Cotangent is 1 over tangent. Well, that's not going to work. Well, cotangent can also be thought of as cosine over sine. Cosine over sine, 0 over 1 is 0. So there we are. Okay, so let's see. Yeah, let's just do one more example. For this section, there are 2, but I think I'll just do 1. So, or maybe 2. Okay, so example. In a square box, a square 3-dimensional box, box of side length S, length S. Find the length of the main diagonal. And I'll draw what I mean by this in a moment. Okay, so we've got a square box. So let's go ahead and do 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's the face of the box. Let's go up like so. It's a 3-dimensional box. Oops. Okay, so what do I know? I know that the length of each side is S. So the depth is S. The height is also S. Each side has side length S, because this is a box, right? So the first thing I'm going to do is I'm going to consider just one of the sides. Namely, let's look at the bottom here. So we have 3, something like so. Well, the diagonal of the bottom, what color should I use for that? Let's use yellow. The diagonal of the bottom will be like so. Let's call this H. I know that each of these, the base is a perfect square. So that's S and S right there on the floor. And this is a right triangle. So if the two sides are the same, this is a 45, 45, 90 right triangle. So we have, how do I want to say this? I just keep it blue. A 45, 45, 90. So what does that imply? Oh, pardon me. That implies a ratio of 1 to 1 to square root of 2 for the side to the hypotenuse. So in order to find the hypotenuse, I just need to multiply to get S. So do you agree in this case? This would give me S is to S is to root 2 times S. But I claim, therefore, that H is the square root of 2 times S, because this is a 45, 45, 90 right triangle. Let me move this to the right a bit. Okay, so now, once I've done the floor, let's consider this height back here in the background. So that height is whatever height it is. And let's consider the square root of 2. So this is the square root of 2s that I just found there on the floor. The height of the box is s. But what I'm going to consider now is the main diagonal of the box, which goes from the back top to the bottom front. So this is going through the box. So let me just go ahead and draw the line solid. So from the back top to the front bottom. This is the diagonal of the box D. So that's what I'm asked to find. Find the length of the main diagonal. This is what we're looking for. Okay, so once again we see that this is a right triangle, because inside this box here, what we have is a right angle for that. Oh, that's a terrible right angle. Let me draw this a bit better. Hopefully you can see that it's a right angle for that triangle, which is oriented along the diagonal of the base. So in order to find the distance, we use a Pythagorean theorem. So d squared is equal to s squared plus quantity, the square root of 2s squared. So d squared is going to be equal to s squared. If I square the square root of 2, root 2 times root 2 is just 2. S times s is s squared. So I get that d squared is actually how many s squareds? Well, I have one of them plus two of them, so I claim that that's going to be 3s squareds. So taking the square root of both sides, I get that d is the square root of 3 times s. And I know it's not negative. I don't need the plus or minus because this is a distance. So, therefore, main diagonal has length, main diagonal, has length root 3 times the side. Okay, so let's use that fact in another example. So example, if a square box has main diagonal of length 7 root 3, find the length of each side. Okay, so we know the diagonal has length 7 root 3. But we also know that that's going to be root 3 times the length of the side, right? So all I need to do then is divide both sides by root 3. The root 3's reduce, and I'm left with 7 on the left is equal to s on the right. So the length of each side is 7. Okay, hopefully this makes sense, and I will see you guys in the next video.